Good morning, everyone. Now it's 9 a.m. in Brazil, and this is the second International Symposium in Transportation Engineering of the University of São Paulo, which is an event organized by the two graduate programs in Transportation Engineering of the University of São Paulo. This is the 8th day of our symposium, and today we are receiving Professor Emmanuel Chailleux from the Université Gustave Eiffel in France. Hello, Professor Emmanuel. It's a great pleasure to receive you here today, and thank you in advance for staying with us today and for dedicating your time to our students and friends. I'd like to welcome all of those who are watching on YouTube now. Thank you all for staying with us today. First of all, I will read a short bio to introduce Professor Emmanuel. Professor Emmanuel Chailleux got his PhD in 2000 at the École Centrale de Lyon in France in the field of polymer science. Since 2004, he has been at a permanent position at Université Gustave Eiffel in the pavement department, and now he's director of the laboratory MIT, which is dedicated to materials for transportation infrastructure. He currently does research on bituminous binder performance, including rheological properties, viscoelastic modeling, aging, and cracking phenomena. He also develops research works on development and characterization of alternative binders derived from biomass. And he is the chairman of the Rhine Technical Committee PIM, Phase and Interface Behavior of Bituminous Materials. So, Professor Emmanuel, it's actually a great honor to have you here, and I'm sure that all of us will enjoy our presentation a lot. Now, I invite Professor Emmanuel for his talk, and right after his presentation, we will have some time for questions and comments from the audience. Professor Emmanuel, please.
So I turned on the microphone before. So thank you very much, Adalberto, for this great introduction. So I will share my screen and we will check if everybody is good. So which one? I will try this one. So is it okay for you? It's okay? It's okay. Okay, so good morning, everyone. So it's 1 p.m. in France. So thank you very much for this invitation. So I will begin my presentation dealing with Okay, Rodrigo say me that I have to come back.
Oui, c'est juste parce que moi j'essaie d'accompagner aussi sur YouTube et ça ne marche plus.
D'accord. It's okay? Okay. So once more, good morning. So I will give you my talk about road asphalt binders. So I would like to speak about conventional standardized specification, but also about advanced characterization of road asphalt binder. So firstly, let me present this new university, Université Gustave Eiffel. It's a relatively new because this university is born in January 2020 and is a result of the merging of a research institute, ISTE, or a long time ago LCPC, Laboratoire Central et Ponts et Chaussées, Université Paris-Est, and a School of Architecture and 3 engineering schools. So this university is a national university. It means that we have different campus across all the France territory. For example, in Paris, Lille, Lyon, but also Bordeaux. So personally, I'm located in Nantes here, where the material for transportation infrastructure laboratory is located, campus of Nantes. So at the moment, we have 17,000 students, 500 doctoral students, 1,200 researchers, and 1,300 support staff. So the plan of my presentation is as follows. So I would like, there are 2 items, standardized specification system, the European system, but also I would like to present you some advanced characterization using linear viscoelastic theory and experimental characterization. But first, I would like to make an introduction, trying to explain the motivation for this presentation on what are the research needs according to specification. So why we are using asphalt in a road construction technique? In fact, it's a very interesting material. This material is between a liquid and a solid. It can be represented by this spring associated with these dashboards. It's what we call a viscoelastic material. It could be liquid at high temperature and very brittle at low temperature, and in between these 2 extreme temperature. It's why this material is very good for road in comparison, for example, to cement concrete, because it has the ability to relax stress. So stress coming from the thermal expansion of material, but also stress coming from the traffic, from the lorry. There is also another advantage, is the fast laying process. We can the traffic can circulate very fast after the laying process, perhaps 1 hour, which is not the case for other type of material. The other advantage is the recyclability. In fact, this material can be considered as a thermoplastic. It means that you have just to heat this material to reduce the viscosity and to recycle this material. So some definition of asphalt. Asphalt could be natural, as you can see on the picture, where we can find bitumen direct from a lake here in Trinidad, or for a mine. But more generally, road asphalt came from petroleum oil distillation, the residue from petroleum oil distillation. The main characteristic of this special material are as following. It is highly viscous or solid at room temperature and liquid at very high temperature. It's an almost non-volatile material, even if there are some debates at the moment about this fact. It's a sticky material, and what it is very important, it's an hydrophobic material. It is perhaps the main property, the main interesting property, the hydrophobicity of this material. And another definition is that asphalt has to be soluble in toluene. So next slide. But let's speak about the future, not perhaps the near future, but the far future. What could be the alternative in the post-oil world? We have to think about it, I think. We have to think about the future. It's why we need to understand deeply asphalt behavior in order to be ready in the post-oil world to mimic this material with other type of natural resources, but also to recycle this material more and more, and to improve this material to make the pavement more sustainable. It is why we need to deeply understand the structure, properties, relationship of asphalt, as we are doing, for example, with the suspension. This graph shows you the viscosity according to the solid fraction of solid particle suspended in an oily matrix, and we see that there is an influence of this solid fraction on the viscosity, but there is also an influence of interaction between particles, and there is influence on the way these particles are distributed across the matrix. We have to understand this type of behavior in asphalt in order to well understand the aging of this material, in order to better regenerate this material in the if you want to recycle more and more wood. And we need to understand this material perhaps to mimic the material in the case of partial replacement, but also in the case of total replacement. So nowadays, all over the world, we have a typical specification system in Europe, in Brazil, in US, which are very useful for civil engineers, but this type of specification system have limits, especially for new material, for non-conventional material. Sometimes this specification can be applied. It's why we have to looking for future specification which will be adapted to all binder types coming from different sources, not only from petroleum oil. For this, we need to have intrinsic evaluation, measuring intrinsic parameters, not empirical parameters. It will help us to promote innovation in the field of pavement construction. So I will now go to the standard used in Europe for road asphalt, beginning by explaining the general properties and performance we need to have for an asphalt binder. So it's a general in every country. We need to have this for asphalt binder. We need to have a low viscosity at high temperature of this material in order to help the compacting, to help the compacting and laying process. we need to have a material stiff enough at intermediate temperature, around 60 degrees, in order to avoid the rotting phenomenon, but not too stiff at intermediate temperature in order to avoid premature fatigue of our material. At a low temperature, we need to have the ability to relax stress in order to avoid cracking. And of course, all these parameters have to resist to aging. So you understand that designing an asphalt binder is like to do the split. So concerning the viscosity, it is generally measured using a rotational viscosimeter at high temperature, between 100 to 160 degrees. It's a very conventional measurement. And what we have to know is, in order to facilitate the process of mixing asphalt with aggregate, we need to have a viscosity between 0.1 and 0.3 Pascal second. It's very important if we want to coat the aggregate with the asphalt binder. Concerning the intermediate temperature, in Europe, we still use the ring on ball temperature, also called the softening point, which is strongly linked with the temperature where the risk of rotting happens. So I don't know if you know this type of test, but we have a ball placed on a small slice of bitumen. We heat up this system, and when the ball crosses the film of bitumen, we have the temperature, the ring on ball temperature linked to the risk of rotting. At intermediate temperature, in fact, we measure the penetrability at 25 degrees, and this penetrability, this well-known penetrability test, is used to define the grade of bitumen. So the principle of this test is to let a needle go into a binder at 25 degrees during 5 seconds, and we measure the deepness of the needle. At low temperature, in Europe, we still use the frost test. So the frost test consists of a film of bitumen placed on a steel plate, and we deform this system at different temperature, and we take the temperature at which this film of bitumen break. So for the aging, we in Europe we just use for specification the RTA40, the rolling thin film oven test, where air is blown across a film of bitumen in some bottle during a certain time at 133 degrees in order to reproduce what's happened during the mixing process in plant. So at the end, we have this type of table where road asphalt can be specified according to different grade. And you see that the properties needed to specify a road asphalt in Europe is just penetrability, softening point, and penetrability and softening point after aging by RTA40. We have also the flash point on solubility, but it is very common properties. So just penetrability and softening point on RTA40 to specify road asphalt. So the grade is defined by the penetrability. the 2030 is a very hard binder, and the 160 220 is a very soft one. The last one is used to make emulsion, for example, and this one is mainly used to make base course, structural course, not surface course. The most common one in France used is a 3550, which is also quite hard. And you see that the penetrability is associated with a range of softening point. And what it is very important, it's what's happened after aging by RTFOT. The mass loss during this aging process has to be below 0.5%. The remaining penetrability in percent has to be above 55%. The penetration on the softening point has not to evolve too much. And the softening point has to remain below 8 degrees for this one, 9 for this one, and 11 for this one. So you see that the specification for road asphalt is very simple in France and is measured using empirical tests like penetrability and softening point. But what it is important in Europe and especially in France is a specification at the asphalt mix level. So I will not go in detail in this specification. I can come back another time for that. But remember that for the mix, the asphalt mix, specification are firstly based on the compactability, is the first step, using gyratory compactor. Our material has to be compacted easily. Then moisture resistance, you're using in France Durier's test. And after rooting resistance, using the French wheel tracking test. And then if it is needed for structural courses, for example, complex modulus, measured at 15 degree 10 Hertz, and also fatigue resistance. But I will not go in detail on this specification at the mix level. I prefer to go on another topic now, which deal with what we can do if we want to make a more advanced characterization of asphalt binder, in order to define perhaps the future specification based on intrinsic properties and not on empirical one. So let me come back on asphalt structure. We know that asphalt is a very complex structure, so which depend on the oil source and also on the manufacturing process. It is more or less a suspension of hard molecule, rigid molecule, asphaltene, in a oily magma composed of resin, aromatic, saturate, and all these molecules could interact themselves in order to form a special structure, which could be between a sol tip, solubilized tip, and a gel tip, here where we have enough asphaltene agglomerate to create a sort of network linked by physical forces. So you see, this material could be considered as heterogeneous, with a complex structure, but it can be also considered as considered to have a continuous molecular mass distribution. There is a certain continuity in the molecular mass distribution. Here you can see on this graph some size exclusion chromatography result. So here we have the normalized size exclusion chromatography signal according to the molecular mass equivalent polystyrene for the saturate, the aromatic, the resin, and the asphaltens. And here the dot line represents the whole asphalt. So you can see that all these distribution overlap themselves. So it seems that we have a continuity in the molecular distribution from very large molecule here to very small molecule here where the saturate are. So it's very important to understand that we have a very complex structure, but also a continuous molecular mass distribution of the asphalt. So the question which arrived now is there a link between mechanical properties and asphalt structure, or more precisely, is there any relationship between linear viscoelastic properties and alpha structure? So I don't know if you use a lot linear viscoelastic measurement, but you have to know that we can measure different type of properties, different type of modulus with linear viscoelastic properties. We can measure the relaxation modulus, the creep modulus, but also the complex modulus. Taking into account that the behavior of linear viscoelastic material is could be represented by the association of spring, where here you have the strain to strain law, and here a dashpot, where here you have the strain to rate, the stress to rate of strain law. Here we have the instantaneous response, here the delay response. And the linear viscoelastic theory says that we can define the relaxation modulus like that in a hereditary integral, where you have here the stress and here the rate of strain, or at the opposite, the creep modulus, or where here you have the strain and here the rate of stress, where you can calculate this strain using a hereditary integral. But I prefer to speak about what we call the complex modulus, which is one of the properties we can measure using the linear viscoelastic theory framework. So what is the complex modulus? In fact, it is a transfer function between two sinusoids. I will explain. When you load a body here with a sinusoidal force, and if you are in the small strain domain, the response in terms of deformation will be also a sinusoidal signal. And we define the complex modulus as a transfer function between these two signals. It means that this complex number will have two parameters to define this complex modulus. The norm of the complex modulus, which will be the ratio between these two amplitudes, and also the phase lag between the two signals, which will be the phase angle of the material, which represents the phase lag between these two signals. If the signals are synchronized, it means that the phase lag is 0, and it means that the material is elastic. And as soon as you have a phase lag, the material is viscoelastic. So, of course, here I have presented a mechanical tension compression loading mode, but you can use different mode of loading. You can use also shear loading, and it is commonly used for binder using what we call a dynamic shear rheometer. And in this case, we measure the complex shear modulus using exactly the same system with sinusoidal force and sinusoidal response. So these linear viscoelastic properties are very useful because it's a mechanical linear behavior of a material which can be measured on a large temperature and frequency range. And here you can see on the screen the complex modulus measured according to temperature for several frequencies, to 1 Hz to 18 Hz. And it is really relevant to the field, of course, relevant to the field for the small strain domain, not for the damage mode, because you can have the temperature we have on a pavement, and we have also different frequency which could represent different speed of vehicle. So very relevant to what's happened on this material on the field. But what we can also observe is that we have a smooth transition from liquid here to solid state. And we can see here on the norm, on the complex modulus according to temperature, but we can also see this smooth transition looking at the phase angle according to temperature. Another type of representation is the black space, where we plot the phase angle according to the modulus. And we see once more that for asphalt road binder, we have a smooth continuity between phase angle, very high value of phase angle, close to 90 degree at very low modulus, to 0 degree at very high modulus. We have a smooth transition from liquid here to solid state. So we think that this mechanical behavior is linked to the continuous molecular distribution. There is a strong link between what we see in viscoelastic properties when we measure these properties from very low temperature to very high temperature at different frequency. There is a strong link between this behavior and the molecular structure. So the question is now, is it possible to have access to the molecular mass distribution from viscoelastic measurement? So we have conducted several research this years, trying to develop what we call the delta method concept. So I will explain this method, and we will see how we can get the molecular mass distribution of asphalt from viscoelastic measurement. So this method was first developed for fusible polymer, and it was firstly introduced by Zanzotto, an asphalt specialist, in some time ago. This method used complex modulus data, of course measured in the linear domain, and the main concept is based on the comparison of observation time versus molecular relaxation time. Here you can see a sketch of molecules which are loaded and unloaded, and the relaxation time represents the time for the molecule to come back to equilibrium. Yes. So the main concept is based on this. If observation time is short or high frequency, in comparison to the relaxation time. So the time to come back to molecular equilibrium. So then the molecule appears to contribute to elasticity. At the opposite, if observation time is very long in comparison to the relaxation time of the molecule, then the molecule appears to not contribute anymore to elasticity, but to viscous behavior. So let's go more in detail, showing you a plot of phase angle here according to frequency. So it is the master curve. I can go later during the question on the master curve construction. So you see that we have a phase angle from 0 to 19. So from the elastic state to the liquid viscous state. And you see that we have a continuous curve linked to the continuous size molecular distribution influence. We think that we could represent all this behavior of this phase angle with a typical type of molecule. In the liquid state, the phase angle is strongly influenced by the biggest molecular structures. So the molecular structures which have very long relaxation time. It means when the phase angle is 90 degrees, when the observation time is very long compared to the longest molecular relaxation time. At the opposite, in when the phase angle is 0, the material is strongly, the viscoelastic properties is strongly influenced by the smallest molecular structure with short relaxation time. It means that the phase angle equals 0 when the observation time is very short, because we are at very high frequency, is very short compared to the shortest molecular relaxation time. So you see, it's a comparison of observation time and molecular weight. So with a measurement at decreasing frequency in this direction, more and more molecules of increasing mass relax. So when I said mass increasing mass relax, I said they don't contribute anymore to the modulus, to the elasticity, and become more and more viscous. So it means that we can consider that the phase angle is linked to the cumulative molecular weight, or in another word, the cumulative weight of fraction of species up to a specified molecular weight. Yes, so it's the basic of the method, the link between the frequency and molecular mass. So of course, it's a big assumption, but we need some time to make assumption that the cumulative molecular weight distribution, what we call the CMWD curve, is proportional to the delta master curve. So it is this equation. The cumulative molecular weight is proportional to the phase angle master curve. But we need, in order to have access to the molecular weight distribution, to transform the frequency of measurement with the molecular weight, and this relationship has been done by Zanzotto 20 years ago. He has built this type of relationship where we can calculate the molecular weight according to the frequency used. At the end, the distribution of molecular weight can be calculated by differentiate the cumulative molecular weight. So it means that to have the this distribution of molecular weight, we need just to differentiate the phase angle according to the frequency or to the molecular weight. So it's a very, at the end, it's a very simple way. But for that, in order to have access to what's happened at very, very low frequency and at very high frequency, we need to extrapolate our experimental data. It's why we use a model developed in my lab a very long time ago, the Wed Oct model, which is a rheological model composed of a linear dashpot, a spring, but also what we call non-linear dashpot. And this dashpot behave between a spring and between a linear dashpot. And here you have the analytical expression of the complex modulus using this model, and you can see that this model can model very well the experimental data for 4 types of bitumen from 50, 70 to 10, 20, and we can have access to a terminal zone, which is very important to determine, you will see, to determine the molecular distribution. So, to calculate the distribution, you need complex modulus measurement, master curve construction of the phase angle, Wed Oct model calibration, the calculation of the frequency of the molecular weight from the measured frequency, and then you have just to differentiate the phase angle modeled by the Wed Oct model. And here you have the result of this. So this curve came from the phase angle differentiation for pure non-edge asphalt. So you see that we have a distribution centered around 1,000 grams per mole, and you see that the peak of distribution order follow the grade of bitumen. Here we have a very hard bitumen, so we have more big molecule than the softer one, where you have more light molecule. So a good idea of the distribution. If we compare the molecular size distribution using this delta method with the conventional size exclusion chromatography method, you can see that we are more or less centered around the same molecular mass, 1,000 grams per mole, but the distribution are not very equivalent. So we have the same bitumen, and we see that the distribution go to a higher mass with the size exclusion chromatography, and does not represent exactly the same distribution, especially for the high mass level. But we know that sometimes in a size exclusion chromatography, it's impossible to break some agglomerate in bitumen, and it is perhaps why we have this difference between the distribution in size exclusion chromatography and in this technique using complex modulus data. So I will show you now some example where we use this method to first see the effect of modification of asphalt with very hard bitumen called asphaltite. So here we have the distribution of asphaltite, which is a very heavy component. And when we mix this asphaltite, which is a natural bitumen, very hard bitumen with soft bitumen here, at 5, 10, or 15%, we see the evolution of the AV molecule increasing when we add more and more asphaltite. So we have a vision of what's happened in terms of molecular distribution when we add hard material to this soft material, which could be very helpful to understand what's happened in terms of dissolution of this material in the other one. The other example is what's happened during aging. And here we have extract asphalt from a loose mix, which were aged during several steps at different temperature. And you see here from the virgin asphalt, from the aged asphalt, step by step, we have more and more very heavy molecules. And each time we see this effect that we create more and more heavy molecule after aging. We can find 4 populations in this type of curve. Here you see you can model this distribution using F1, F2, F3, or on F4 population, and we can follow this population according to aging state, and we recognize the result we have also with the size exclusion chromatography. It means that nothing happens for the lower molecular mass, but what it is very important during aging is the increase of the highest molecular population, certainly due to some association of molecule during aging link with the increase of polarity of the medium during aging. It's a typical result we find with the delta method, which is very well known using conventional method. So if we look at the effect of lab aging on grade, we see that we can distinguish between grade and aging also. So here we have a very soft binder, and here a very hard binder. And we recognize that the lab aging conduct to once more an increase of the highest population, and the lowest population decrease in percentage. So we use this lowest molecule to increase the highest molecule by molecular association. So chemical or physical association. If we look at the population content with aging and with the grade of bitumen, we recognize a typical result also we have with the SARA analysis, for example. It's this result is that what it is important, it's the 2 intermediate population. So during aging, but also during the changing of grade, there is an exchange between these 2 intermediate populations, while the lowest and the highest one remains relatively stable. So very interesting result, which confirm what we see with other techniques. So we are very confident with the delta method techniques, and we think we can have very good information about the molecular structure variation with aging, and with also lots of other parameters. So finally, I want to finish with the effect of rejuvenation with the delta method. So in black, you have the distribution of asphalt binder extract from a very old road. So it is a typical distribution calculated from the delta method of a very old bitumen with the population of high mass which dominate the overall distribution. And when we add regenerator, so in this case 3 regenerator was used, we see that this big molecular structure is destroyed in favor of another intermediate molecular structure, and we see that another population appear here in the lower mass domain, which is linked to the regenerator itself, which is a very low viscosity material. So I think now it's time to conclude. First, I want to recall that the University Gustave Eiffel is a new university. I work in a laboratory called Material for Transportation Infrastructure, and we were 1 year ago ISTE, and some years ago Laboratoire Central des Ponts et Chaussées, but now we are a university. During the introduction, I tried to explain that due to the viscoelastic nature, asphalt binder are very well adapted to paved road. Even if we need to fully understand the structure properties relationship of this material in order to be ready for future challenge in road construction techniques, especially when we are trying to find non-conventional material, when we try to recycle road, when you try to understand the aging of our pavement. The specification for asphalt in Europe, as you have seen, is still based on empirical properties. But you have to know that the specification system in Europe is more focused on the asphalt mixes performances. I show you a new method, the delta method. It's a new way to interpret linear viscoelastic properties. In this method, we not only take some typical point on the curve at certain temperature, certain frequency, but we are observing the overall viscoelastic spectra in order to be close to the internal molecular structure of asphalt. And you have seen that we are able with this method to fully capture aging, modification, rejuvenation, and we hope we can go further with this method, and perhaps up to perhaps a specification. Thank you very much for your attention. So now I'm ready to answer to some question if there is some question.
Thank you very much, Professor Emmanuel, for your great presentation, a very nice presentation, especially this topic relating molecular structure of the asphalt binder and rheological properties. Very interesting. We have some questions. Can we proceed?
Yes, of course.
Yeah, a moment. First question is asked by Andrisi, who is my student here. She asks about binary specification in Europe. What is, in your opinion, the future of the binary specification in Europe? Is it moving towards a performance-based specification, such as the American one, or will it keep based on penetration and ring and ball and so forth?
I think so. Specification in Europe, specification at the binder level is mainly used to sell and to buy bitumen. Yes, But what it is more important for road owners, for example, is the specification at the mix level. So I think in Europe, our effort has to be has to improve the mix performances, especially including edging, but at the mix level. Because we, but concerning asphalt binder, we need to understand more what's happened at the material level itself. So I'm not sure we have to improve specification at the binder level. I'm not sure we have to move from empirical 1 to, for example, the PG grade. I think we have more to work at the mix level, in fact, for specification, for research, for the understanding of the material. Of course, we need to find more intrinsic evaluation and to go to do more than empirical tests. I don't know if I'm clear or not.
Yeah, yes, perfect. Thank you. I have another one. Just a moment. Emmanuel, if you could stop the screen sharing, please. Okay. Right, may I proceed?
Yes, I stop. I think I stopped to share.
Okay. We have another question from Mateus, who is also a student from our program, which is the percentage of modified binders used in France in relation to the whole market, binder market in France.
So I don't know this the percentage, the exact percentage. Perhaps it's between 5 and 10%, but it's a very small amount of the material used in France. It is especially used in surface courses, and using also for porous asphalt in surface courses on big motorway. But at the moment, it's a very small amount of the market.
5 to 10% roughly, right?
Yes, but I'm not sure. Yes. Okay. Please, we have to verify this number.
Okay. We have another question from my student João. He wants to know how Europeans are dealing with the characterization of modified binders. He asks, are they managing to characterize such materials by using penetration, ring and ball, and so forth?
Yes, I understand this question because the US specification system and the European specification system have problem with the polymer modified bitumen because what we know is that polymer exhibit a very special behavior in the high strain domain. Yes, it's why in order to promote this type of modified bitumen, we need perhaps to go in the non-linear domain, in fact. And if we remain in the small strain domain, it will be impossible to see the improvement of a bitumen with a polymer. I don't know if we have developed several years ago here at Université Gustave Eiffel a 3-point bending test on pre-notch asphalt sample, where it's a test inspired by the linear fracture mechanics, and we try to assess the resistance of the material to a crack. And with this test, we see that the polymer modified bitumen behave better than plain bitumen, than pure bitumen, even if, for example, the bending beam barometer gives the same result. Because the bending beam barometer is performed in the small strain domain. So in the small strain domain, polymer doesn't play a big role, in fact. But as soon as you have very high strain, you loaded with the matrix the polymer nodules, and you can have very interesting results with polymer. So sometimes the performance depends on the test.
Okay, thank you very much. I think we have more questions. Another one from our friend Camila. She asks, have you compared the variation of the data of the delta method, coefficient of variation, for example, compared to the conventional methods?
I'm not sure to understand the question.
Okay, may I repeat? She asks,
it's about the precision. It's about the precision of the method.
Yes. Camila, do you want to open your mic?
Hi, Emmanuel. Yes, it's pretty much related to the repeatability and the variation itself.
So at the moment, we have not made this study of variation, coefficient of variation. What I can say is that we have tested perhaps several binders from different sources, coming from the field, coming from lab aging, coming from different grade, and every time we find the same type of behavior. It means that a pure bitumen, non-age, is always represented in terms of distribution like an unimodal distribution. And as soon as you have a material age and very age, you pass from a unimodal distribution to a bimodal and then to a trimodal distribution. And so we have not strictly done precision or repeatability test, but we can recognize this typical behavior each time. And yes.
Okay. We have another question from Camila. Emmanuel, you are a very well-known person with respect to the biobinder studies. Do you consider the same specification used for asphalt binders to test the biobinder materials?
So at the moment, I think we are not ready to use the same type of specification for biobinder and for conventional petroleum binder. But it is what I said during the introduction. We need to go to a system of specification. So at binder level or at the mix level, adapt to all type of materials. Because for example, we made a full-scale test using BioBinder here with our full-scale carousel full-scale test. And before we make some design in lab using the French specification system. The French specification system said that our biomaterial will be destroyed in 1 month. And we discover at full scale that it did not happen. Why? Because the specification system is not adapted to non-conventional material. Yes. So we need to find a specification system adapt to all material, representative, relevant to the field, in fact, which is not the case. So at the moment, for example, in France, we know perfectly our specification system and we know how to apply it on field. But as soon as we have a non-conventional material, the thing goes wrong. So it is very important because if we want to promote new material, new innovation, we need to have a very relevant test on lab, which is not the case at the moment.
Okay, we have another question from Leni, our friend Leni. She's saying, very good presentation.
Thank you.
Interesting correlation between phase angle and molecular weight. So she asks, she's saying GPC shows a difference between agglomerates and high molecular size. And so she asks this question: have you already compared these two techniques?
I'm not sure to have fully understand which techniques, size exclusion on the delta method?
GPC and delta method.
Yes. It's what I present in one slide. I present the size exclusion chromatography. And the other name of size exclusion chromatography is GPC, gel permeation chromatography.
Okay.
So we have compared it. The comparison is not so good in terms of size of the distribution, but it is centered around the same mass, 1,000 grams per mole. So we have not the same result, but it does not mean that GPC or SEC gives the exact distribution. For example, we know that in GPC or size exclusion chromatography, we measure some molecules around 100,000 grams per mole, which is impossible. We can have this type of molecule in bitumen because, for example, asphalt 10, the molecule is asphalt 10 is around 550 grams per mole. So it means with chemical technique like or physical technique like GPC or SEC, we measure agglomerate of molecule, not only molecule, in fact. So all methods have a default. And I think we can compare strictly GPC and delta method, but we can use it if we understand what we measure. And in the delta method, we have a direct access to the effect of packet of molecule on the mechanical behavior. Yes, perhaps we have not individual molecule, but we have effect of individual packet or family of molecule. Yes. But we need to understand more, of course.
Okay. And I think we have one more question asked by Carlos Alberto, who is also my student. Is there some measured relationship between the delta method and performance of asphalt mixtures? I mean, actual relationships.
We are at the beginning, but for example, we know that some times ago we make a comparison of the relaxation spectrum of asphalt measured by viscoelastic properties and compared to fatigue properties. And we have a strong relationship between the form, the shape of the relaxation spectrum and the fatigue properties. And we know that the relaxation spectrum is very close to the molecular size distribution. So we can expect in the future to show that there is a strong relationship between the shape of the distribution and the fatigue performance. But we have to do this job.
So at this moment, you are using this delta method only, you are using more for material comparison, right?
At the moment, we are trying to understand what we can do with this method. We are testing the response of this method with different binder modification, binder aging. Yes, and we are going step by step. Okay,
perfect. First at the binder level and then at the mixture level. Okay.
In fact, the idea, this distribution is calculated from the phase angle, and we want to understand what's happened on this distribution. But I think at the final stage, we will come back to the phase angle to have a more direct analysis, in fact. But knowing that this phase angle is linked to the molecular distribution. Yes. So at the end, and Rodrigo is working on this. Rodrigo Siroma, which is a PhD student here, coming from Brazil, is working on that at the moment on the phase angle itself.
Okay. Well, okay, Emmanuel, just checking if we have more questions. I don't think so. We don't have more questions.
Good.
So, good. Very good questions. Good number of questions. And so thank you very much, Emmanuel, again, for staying with us. It was a very, very nice presentation. We learned a lot with you. And I need to say officially, on behalf of our 2 graduate programs, thank you very much for staying with us, for sharing your experience with us. And we hope to have you for the next edition of our symposium next year. It was a great pleasure to meet you, to stay in contact with you during this session. It was an honor to be the chair of your session. And we received lots of people congratulating you on YouTube for your presentation, which was really very nice. And so thank you very much again. And I also want to thank all of those who helped me during this transmission, including Ana Paula, Camila, Carlos, Rodrigo, and especially you, Manuel, for staying with us. So we are finishing this presentation, this session, and I'd like to invite all of you for the next one today in the afternoon at 3 p.m. with Professor Huang from the 20 University. Special thanks to the audience too for the questions and for the comments and everything else, for the attention. So thank you all. Bye-bye.
Thank you. Bye.